Nice to meet you all. Thanks for coming today. My name is Phil Hans. I am going to be teaching you the first 8 or 9 lectures or so. Why are we interested in semiconductors? Well, it's an enormously powerful, enormously profitable business. Electronics is underpinned by the semiconductor industry. In order to make electronics, in order to make the microchips that are inside your mobile phone, you need to understand semiconductor physics. And it's the semiconductor industry, i.e. the industry that helps you to make those microelectronic components, is, to use an American example, the biggest industry in the US. It's also one of the largest industries in many, many other countries as well. It's also massively growing at a very rapid rate. If you look at this breakdown of different sectors, you see electronics is by far the biggest one, and it's going to set to increase even larger over the next few years as well. So it underpins the entire electronics industry. You can't have a computer or mobile phone, all these sort of electronics device industry. You cannot have any of those devices unless you've got microelectronic components within them. And this course is all about what is inside those microchips, how do we make them, and how do they operate. The UK plays its part in this. In fact, it has a very strong history in electronics and semiconductors. So the UK semiconductor industry, and I use that word deliberately, so the manufacture of chips, employs a few thousand people across the UK. It brings in several billion pounds worth of revenue to the UK. At the time of writing, I think this might be slightly out of date, there were about a dozen or so semiconductor manufacturing plants. We had the largest share of Europe's semiconductor market complete. And there are several companies here. Those of you who perhaps might be on an electrical engineering scholarship might recognise a couple of names here. We work very closely with these companies. I collaborate with Semifab, Analog Devices here in Edinburgh, ST Microelectronics. These are big, big names in the semiconductor industry, and they have centres here in Scotland and close to Edinburgh. The electronics industry, upon which the semiconductor industry is based, is even bigger. So here you see annual sales of tens of billions of pounds worth of stuff sold across the world. 250,000, 250,000 people, 45,000 of which are in Scotland. We take an unusually large share of this industry. So not only is it strong in the UK, but it's particularly strong in Scotland. We're the 5th largest producer of electronics items in the world, and certainly at our peak, I think you would argue that some of our numbers have dropped in recent years, but at its peak in the late 80s, early 90s, we were accounted for about 6% of the UK manufacturing output, or 12% of in Scotland. So much so that Scotland had its #1 export was used to be whiskey, and now it was in the late 80s, early 1980s, sorry, it was overtaken by electronics items. So if you bought a laptop or a computer in the late 80s, and I'm guessing a lot of you weren't around then, but I certainly was, but at that point in time, when you were very, very young, or perhaps just beforehand, 28% of Europe's computers were made here in Scotland, just in Scotland, and 7% of the world's PCs were made here, and even more, nearly a third of all the world's laptop computers or notebook computers. This was driven by something called Silicon Glen. You've heard of Silicon Valley in the US, where all the big Google names and all that, Microsoft, are all based. Well, in the late 80s, or mid-80s, early 90s, there was a massive investment in Scotland in semiconductor and electronics companies. And in its peak, it was huge, and this focused area of electronics here. Now, since then, we're not so big in manufacturing. However, what has remained from that legacy is electronics design. Now, to build a phone or a chip for a phone requires enormous investment in buildings and fabrication equipment, which Jay will be telling us all about in a few lectures' time. But to design it can be done anywhere in the world. You need the intelligence and the know-how to design it, but it can be done anywhere in the world. So the UK is a big centre now for design, less so of manufacture. Okay. Now, our little part here in the University of Edinburgh is this building here. It's where all 3 of us happen to work, all 4 of us happen to work. You recognise the building? It's called the Scottish Microelectronics Centre. If you've ever stood waiting for a bus at the KB bus stop, this is the building directly opposite you. The bus stop is on the left-hand side, looking at it. So the tall building on the left is offices, but the big flat area, single-storey building at the side is a large clean room facility where we electronic devices. Okay, we're not making bleeding-edge chips to go in your phone, not yet, well, not ever, because to do so requires billions and billions of investment to get the very bleeding edge of technology. What we have is state-of-the-art circa 15 years ago, which may sound old-fashioned, but it's not. But what we're doing is we're adding extra functionality onto the leading edge electronics. So we're not making the world's smallest transistor, but what we're doing is designing stuff and building it on top of the world's smallest transistor to make more interesting devices, sensors and interesting researchy devices and things. So we have a world-leading facility here, and there's more than £10 million worth of equipment there. If you're interested in this sort of thing, if this course whets your appetite, then there are opportunities potentially to work with us in final year projects, BEng, MEng projects, perhaps working with some of the Scottish semiconductor companies in your MEng placement, for example. So good opportunities to continue with that if you want to. So it's a big, big clean room environment. If you're making things that are really, really small, they have to be really, really clean, because one speck of dust would land on the top and would ruin the entire device. So we work in these super clean environments. They're much, much cleaner than any hospital theatre. They're much cleaner than where they make satellites for NASA. These are sort of a few thousand times cleaner than that. So we have what we call a class 10 bays, which is 10 particles per cubic meter or something, which is ridiculously clean. So no dust, and you have to dress up in these silly outfits to make sure that we're all the dust and dirt. We are by far the dirtiest things to enter into these rooms, so we have to get ourselves suited up. So this is where the microelectronics device fabrication occurs, and some of that's happening here at the SMC. So the technology's got smaller and smaller and smaller. Integrated circuits have got more and more compact, and there are various sort of high-impact images throughout the 80s and 90s, and as we wondered at how small these things really could go. So this is where we are, roughly speaking, at the moment. I don't know if any of you are keen computer builders or anything, but if you you had enough money and wanted to buy a kind of a bleeding-edge computer processor chip, you might be able to buy one of these, something called 10 nanometer technology. It's pretty much the state-of-the-art for home computing anyway. I haven't got one quite this good. I've got a 14 nanometer one, but what's 10 nanometer technology? It's something called the Ice Lake processor range. Anyone know how many transistors are in one of those chips? I'll give you some scale. This chip here is about an inch or so square, with the actual integrated circuit inside less than a centimeter square. Anyone know roughly how many transistors might be on there? Looks like you've got an answer waiting to come out.
7 billion.
7 billion. A few more? Anyone else? You're pretty close. Pretty close. So it's about 10 to 15 billion. You're about halfway there. 7 billion is what 14 nanometer technology is on. I've got a couple of years ago bought a decent computer, and it had that technology on it. The latest ones are about 10 to 15 billion. The kind of leading edge that's not yet commercialized but is trying to be brought out into the world is 7 nanometer technology, which contains, they reckon, 20 billion transistors. So just put a scale of that, it's about 100 million for every square millimeter. It's incredible technology. And, okay, with throwing these numbers around, they're big numbers or very small numbers, depending on your point of view. How big is a nanometer? How big is 10 nanometers, this technology that we're talking about, that we can manipulate the 10 nanometer scale? Anyone has got a clue? How thick is a human hair? Anyone got a rough guess for numbers here on an idea of scale here? How thick is a human hair? You can feel it with your fingers. Go on, someone have a guess. Someone's too shy. I'll pick on you, Jamie, that'd be really evil. Do you know how thick is a human hair?
I don't know, 50 microns?
Yeah, well, 10 to 20, yeah, something like that. A few tens of microns thick is a human hair, depending on how grey your hair is. And it tends to get thicker as you get older, apparently. So that's about 10 microns. So obviously that's 10 to the micron, that's 10 to the minus 6. That's obviously much bigger. Red blood cells, anyone? Oh. So anyone, whereabouts in this scale do you think? So how big is a silicon atom? So if we're making transistors out of lumps of silicon, it's got to be bigger than a silicon atom, right? Right, but how big is a DNA molecule? Anyone got any ideas? Or a virus, or a cold virus, or a red blood cell? Sort of things you get an idea of scale for. So just to tell you, I've had to update this slide this year because 10 nanometer technology is actually getting pretty close to the size of a DNA molecule. It used to be that I highlighted D, the size of a cold virus, because they're about 20 nanometers or so. But DNA molecules are even smaller, and we're getting close to that now. So here we go. Human hair, red blood cells, they're about 6 microns. 600 nanometers for bacteria. Here's your cold virus, nasty looking thing, 20 nanometers across maybe. DNA molecule, the width of a DNA molecule, the separation between the DNA strands is only a couple of nanometers. And we're kind of in that scale there. And then if we go a little bit smaller, this is a scanning tunneling microscope image of a crystal of silicon atoms. Each one of those little blobs represents the silicon atom. And they are approximately 2.5 angstroms apart, so that's 10 to the minus 10. So we're not far away. Think about it then. 14 nanometers is about 56 atoms, so 10 nanometers, even less than 50 atoms thick. So we're getting right down to a fundamental limit here. I want to talk to you a little bit about reasons why. Why on earth do we have this insatiable desire to make things smaller and smaller and smaller? And cheaper and cheaper. Well, making things cheaper makes sense. That's everyone likes things that are cheaper. But by making things smaller, we can actually get a higher productivity. So when we make microchips, we tend to make them on large silicon wafers, and we can get many chips on one wafer. And if you have more chips on a wafer, stands to reason you're going to make more money, because you can divide that wafer by 1,000 instead of 100 and get more money. So it makes more sense for the manufacturers to stick more chips on a wafer. It also means that things get faster, because electrons have to physically move from one end of the chip to the other. They have to move around. That controls the speed of your processor ultimately. So if you've got shorter transit times, shorter distances, stands to reason your device is going to be faster. Lower power consumption. Smaller electric fields are required to drive electrons across smaller devices. So you don't need a big voltage, therefore you can have a better battery power. Higher yield. I'll come back to that in a minute. New products. So just by fact that things go smaller means they suddenly become more useful. So phones, when they first come out, mobile phones, weren't very mobile. You know, carrying around a large battery pack with you and an antenna. It was a suitcase-sized phone originally, but they got much, much smaller these days. Now, mobile phones, a bit of a trend bucking system, because across the 80s and 90s, mobile phones got smaller and smaller and smaller. This is about the time that I adopted the mobile phone, when it was pretty much at its smallest. I could tuck it in the inner pocket in your jeans there. I could tuck it in there, no problem at all. And now they're huge. They're big phones. They got bigger and bigger and bigger. That's not things getting smaller. What it kind of is, the processors got smaller and smaller and smaller. What it's allowed us to do is to put more functionality into that